All right, so for this lesson, we are going to be looking at subsets. These are some challenging subset questions, so they're called advanced subset problems. In the past, we have looked at taking some numbers and creating a new number. So how many ways can we arrange these numbers so that we create a new number? These look similar, but they're a little bit different. We're looking at what are called subsets. So the way to think of a subset is I have my big set here, and a subset is a group that lives within this subset. So for this example, we're given the set 1, 2, 3, all the way up to 21, and we want to determine how many subsets of 7 elements can be made in which 15 is the second largest odd number, or 4 is the smallest even number. Now, this is what I mean by a subset. So all of the numbers 1 to 21 live in the big circle. So in the big circle, all of those numbers live in here. 1, 2, 3, all the way to 21. They all live in this big circle. Now, a subset would be a smaller group of those numbers. So within that group, maybe I have 1, 2, and 3 only. The other numbers are still living out here. So they're all still within the set, but I have just taken some and circled them off in a little set. And that's what a subset is. And that's what we'll be looking at here. Now, with that being said, we want to think to ourselves, does order matter here? If I look here, if I have 1, 2, 3 living in this subset, or if maybe I have 3, 2, and 1 living in that subset, those are the same thing. So what happens is the order doesn't matter when we're looking at a subset. That's an important piece to note here because it helps us to decide, should I use permutations or combinations? So when I'm looking at subsets, order doesn't matter because I'm just taking some of the sets and having them live here. The order in which they're selected there doesn't matter at all. So order doesn't matter here, and that's why. Okay, so let's go through this example. I just want to go through it nice and slow so that people can ask questions along the way if they have any at all. So we're given the set 1, 2, 3, all the way up to 21, just whole numbers. How many subsets of 7 elements can be made in which 15 is the second largest odd number, or 4 is the smallest even number? So we have a lot going on here, and we just want to break it down. So we're going to look at 2 cases. The reason why we're going to look at 2 cases is because of this word or here. We want to look at the situation where 15 is the second largest odd number, or 4 is the smallest even number. So that's what we'll be looking at here. Let's start by looking at case A, where 15 is the second largest odd number. Now you'll notice that we have some lines drawn here. This is just because we are trying to ensure that in our subset that 15 is the second largest odd number. So we do need to consider which values are smaller than 15, which numbers are greater than 15 and also odd. Those are pieces that we just need to consider. It does not mean that order matters with how we approach these. So just to be very clear, the order still doesn't matter. It's just to help us ensure that 15 is the second largest odd number, or that 4 is the smallest even. So let's think about our options for all of these different positions here. So 15 has to be the second largest odd number. So what I've done is I've just drawn out 7 little spaces, and we've put in 15 as the second largest number. Now it's the second largest odd number. So the numbers that could be greater than it and also odd are 17, 19, and 21. We're just going to look at those because the larger even numbers, they could be picked with all of the other numbers. There's no conditions that impact the larger even numbers, so we're not going to worry about them right now. We're just going to worry about the larger odd numbers. Now, everything smaller than 15, it doesn't really matter. There's no real conditions that are stopping us. So in here, we will require 5 numbers that can't be 15 because we've already used 15. And it also can't be 17, 19, or 21. This is because we've already accounted for picking 17, 19, or 21 over here. Again, the reason we had to look at them separately is we can only have one of them in there. We can't risk accidentally having 17 and 19, or else 15 isn't the second largest odd number. So that's why we just need to look at them separately. So that means in here, 5 numbers that cannot be 15, 17, 19, 21. It means we have 17 numbers to choose from for those 5. Those 17 numbers are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 16, 18, 20, 17. So sometimes I do think it helps to actually count them out on your fingers just to ensure that you haven't missed any when we have certain numbers living in a different part of the subset, or they just have to be counted separately. So we have 17 to choose from, and we would like to select 5. Now, again, order doesn't matter here. We're just drawing out the lines just to ensure that we know that 15 is our second largest odd number. But the actual order doesn't really matter too much. So we will require those 5 numbers. Then for the 15, there's one number for the 15, and we're going to choose that one number. You don't have to include this because it's just equivalent to 1, but sometimes writing that in as a part of the process helps people, but you do not need to include it if you don't want to. You can just say we have one option for 15 and it's 1, but that's where that 1 comes from. Then we need to, that is for this part, that is for the 15. Then we need to figure out how many ways we could choose one of 17, 19, and 21. So there's 3 numbers there. We would like to select one of them. There we go. So now let's put this into our calculator. So 17 choose 5 is 6,188. We multiply because we're using the word and, because I need that first bit and the next bit and the last bit. 1 choose 1 is just 1. And that's because it has to be a 15. Again, you don't need to include that part. It does just help some people understand. And then we have 3 choose 1, which is 3. There we go. So now I'm just going to put this in my calculator. And I get 18,564. So that is our total number of subsets, in which 15 is the second largest odd number. So here, so the total number of subsets of 7 elements, of which 15 is the second largest odd number, is 18,564. Lots of subsets. Okay. Any questions so far before we move on to the second piece? We're going to continue with this example, but I just want to check in. Okay. Where did I get the first one from? So this one comes from all of the possible options that could go here. So all of these possible options include, let me just do this. All of the numbers that could go in this area could be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Can't be 15 because 15 is already here. 16. Can't be 17 because 17 is already here. 18. Same with 19. Can't be 19. 20. Can't be 21 because 21's here. This gives us 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17 different options to choose for this chunk. And we only need to choose 5 of them. So 17, choose 5 of them. That's where that comes from. Hopefully that cleared that up. Okay, so we'll continue on and hopefully more examples help to clear things up even further. Okay. So that's the first part. Remember that the question says second largest odd number or 4 is the smallest even number. So that means we have to look at both options. So now let's look at 4 being the smallest even number. So 4 is the smallest even number. Again, we have written out 7 spaces. This does not mean that order matters. We're just trying to ensure that 4 is our smallest even number. So it just helps us to orient ourselves and keep 4 as the smallest even number, not accidentally count something we shouldn't have. So what we'll do is we'll put 4 here at the front just to ensure it's our smallest one. Now, everything in this area could be any number except 4 or 2. It can't be 2 because if 2 was included in the subset, 4 would no longer be the smallest even number that's living in the subset. So we can't have 2 either. And then we can't have 4 here because we've already accounted for it right here. So we can't include it twice. So now in here, this could be 1, 2, oops, not 2, 3, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21. So how many options do we have? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19. So that is 19 choices. 19, I guess I should say 19 options. 19 options. And we have 6 spots that we need to fill. So from this 4 over here, there's one option, and we're just going to choose that one option. Again, you don't need to write 1, choose 1 because it's just 1, but some people like to add that into their process. And we need to choose the other numbers. So we have 19 to choose from, and we want to choose 6. Why did I stop at 21? Because in the set I'm using, it only goes up to 21. So in the question, we can only use the numbers 1 to 21. That's why. So just from the question, it would tell you which numbers you can use at the very beginning for any question like this. All right, so now I can put those in my calculator. So only one way to ensure 4 is picked, which makes sense, but that's where that comes from. And then 19 choose 6 is 27,132. So we just get 27,132. So that's how many ways we can have 4 as the smallest even number. Okay. So now what we're going to do is we have to account for double counting, right? Because it is possible to have both of these situations at the same time? Just a quick question I want to address. Why do we do 1, choose 1 again? Because for this spot right here, there's only one option, which is 4, and we're going to choose one option. You do not need to do the 1, choose 1. If you're comfortable just saying, okay, there's only one way to choose that 4, and then multiply by this, that is totally fine too. But it's just because there's only one option for that spot, and we're going to pick the one thing. So just like we've done before, we need to ensure that we've accounted for double counting. When we're looking at different cases, sometimes a particular situation occurs in both, and we've accidentally counted it 2 times. Now, we could certainly have a situation in which 15 is the second largest odd number and 4 is the smallest even. That could certainly happen that both of those are occurring at the same time. So we must account for this. And to do that, we determine how many 7-element subsets have both 15 as the second largest odd number and 4 as the smallest even number. So we want to look for the situation in which they include both. So what we're going to do again is we're going to line up some spaces just to ensure that we're looking out for which ones are the smallest, which ones are the biggest. And now we're going to determine how many options we have for each spot. So for this spot here, there's only one option because it has to be a 4. So I'll explain it this way just in case this makes things easier for people. So for right here, there's only one option for this because it must be a 4. Now let's look at the last spot. One trick to these is to look at the spots that have more restrictions first. That way we can understand what must go there and then fill in the spots that have less restrictions. So here, there's only one way to ensure that a 15 goes there. Now 15 is the second largest odd number. To ensure that that's the second largest odd number, we can only choose one odd number bigger than it. So here we can choose from 17, 19, or 21. So there's 3 options for those, and we have to choose one of them. Now for this middle bit. This middle bit does have some restrictions on it. This middle bit here cannot include 2 because 4 must be the smallest even number. It cannot include 4 because we've already accounted for 4. It can't include 15 because we've already accounted for 15. It can't include 17, 19, or 21 because we've already accounted for those. So how many options do we have for here? We could have 1, 3, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 16, 20, and I think, I forgot 18, my bad. There we go. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15 numbers to choose from. And we're going to be choosing 4 of them. So that means that our total number of our total number of subsets with 7 elements, for which 15 is the second largest odd number and 4 is the smallest even number, would be 15, choose 4, 3, choose 1. You could also include the 1s here for the 4 and the 15, but I just want to show you what it looks like without that, if that is clearer for people. Then we put that into our calculator. So 15 choose 4 is 1,365. 3 choose 1 is 3. So 4,095 is our answer. So that's for our double counting. These were the ones that we accidentally counted in both case A and case B. So to find our total number of ways, so our number of subsets, we want to include all of the ones where 15 is our second largest odd number. That would be 18,564. Then we want to add all of those ones in which 4 is our smallest even number, which is 27,132. And then we need to subtract the ones that we accidentally double counted, which is 4,095. So in total, we have 41,601. Are there any questions at all? I do want to do another example too, but I just want to check in. No, we're okay?